Welcome to Train Signal. I'm Ross Bagurtis, and in this video we'll be discussing Wireshark basics. And what I'd like to do is give you a brief overview of Wireshark, show you how to install it, select the proper interface to capture on, and then do some basic Wireshark captures of a ping, of a three-way handshake, and of a website. Now the segment, the packet, and the frame. These three datagram types are going to be exactly what we see in Wireshark, and it's going to be what we use to troubleshoot in Wireshark. At the transport layer, we have the segment, and in the segment we have application layer data, and then a header containing the source port, destination port, and then other info about whether this is TCP or UDP, and the specifics about that protocol. At the network layer, we have our packet, and in the packet we put our segment from the transport layer as the data, and then we have a network layer header which contains the source IP address, destination IP address, as well as some other info that helps IP work. Last, we take our packet at the network layer, we make that the data of the data link layer, and here we're going to have a destination MAC address, a source MAC address, and other info about that data link layer protocol. Now again, this frame is going to look like a Ethernet frame. Most frames at the data link layer look similar, but each protocol is going to use something a little bit different. So if you're not using Ethernet at the data link layer, your frame may look different. When we put it all together and we look at the complete datagram, we're going to have data from the application layer, followed by a segment header, followed by a packet header, and then followed by the frame header. The first piece of information to arrive on Wireshark is going to be the frame header, actually. Then the packet header, then the segment header. And in Wireshark, what we're going to see is that the frame, packet, segment, and data are all ones and zeros, and Wireshark is going to represent those as hexadecimal values. Now, each one of these hexadecimal values down here in the bottom represents 4 binary bits. So each one of these is 4 binary bits, and we use the hexadecimal just to make it easier to represent and to see graphically. Now I'd like to demonstrate an overview of Wireshark. And what I'd like to do is show you where you can go to download Wireshark, how to install it, and what settings you should make while you're installing it. And then we're going to launch the application and take a look at how to select the proper interface for capturing. After we select the proper interface from capturing, we're then going to use Wireshark to capture packets, and we're going to take a look at the different windows inside of Wireshark and what of the little features are in each window. To download Wireshark, I'm going to open a browser and browse to wireshark.org. Now, Wireshark is an open source application. They are owned by Riverbed, and Riverbed has some enhanced products that you can purchase to help with your network troubleshooting and packet capturing. However, the freely available Wireshark application is pretty outstanding. They make it for Windows, Macintosh, and Linux. And you just click on the download Wireshark link and then select the version that's appropriate for your version of Windows. I'm using 64-bit Windows 7, so I'll download the Windows 64-bit installer. Now, Wireshark requires 2 applications to function properly on Windows. One application is the Wireshark application itself, and the second is a program called WinPCAP. And WinPCAP is an application that actually hooks onto your network interface card internally, so that it can capture the packets and take an image or make a mirror copy of the packets that are leaving and being received on your network interface card, so it can then send them to Wireshark to be displayed. Now that Wireshark is downloaded, I will click on the file I downloaded and say yes. Now, as I go through the wizard here, I'm going to select all the default settings. Since Wireshark is open source, they do not use advertising, so it makes it very nice to set up. You don't have to worry about installing any extra ad bars or search engines or anything like that onto your workstation. You're just going to get a basic, clean install of this really nice application. So we're just going to go through the wizard and keep all of the default settings. Here is the second application that I mentioned. This is WinPCAP. You will definitely need to make sure that WinPCAP is installed for this to work right. And again, if you just follow the defaults, it will install perfectly fine. Once we're ready to finish, I'm going to click on Run Wireshark right away. And then I'll close my web browser. And that will bring me to my Wireshark Network Analyzer window. Let's make that full screen for us. And what we have is our main screen now. And in our main screen, we have several options here. We have our capture window. In our capture window, we can bring up an interface list. We can look at the interfaces that are available for capturing here and select one and click Start to begin a capture. Or we can choose some detailed options about our capturing. Down at the bottom, we have a window for help sections. In the middle window, we can open previously captured sessions. And then over here on the far right, we have some online resources that we can use. What we're most interested, though, is capturing packets. So we need to know which interface to use to start capturing on. There's a couple ways we can determine this. My favorite way is first to take a look and see which interface has a default gateway configured. The interface with the default gateway is the one that's connected to the internet, and 9 times out of 10, that is the interface we want to use to capture traffic on. Now, there are other times when this may not be the case, and in those times you'll have to just determine based on how your workstation running Wireshark is connected to your data network. If we take a look at ipconfig all, to do that we need to open CMD, and then I'll type ipconfig/all. This will show us all the interfaces on our workstation. And the one that's connected to the internet, which is the one that I'll be doing my capturing on, is the only one that has a default gateway configured. I may only have one default gateway configured on my workstation. That interface happens to be right here. I have default gateway configured 192.168.170.2, and that is on the interface that has the description of Intel Pro/1000 MT. So I want to be doing my captures on that Intel Pro 1000 MT network connection. The other way to take a look and find out what interface you want to capture on is if you select your interface list. The interface list will, the one that is actually moving traffic, you'll see that packets increase in that particular interface. So this packet count is going to increase over time, whereas other interfaces aren't going to have any traffic at all. So if I click on my web browser again to just generate some traffic, we'll see that my packet count went up to 64 here now, meaning this is the interface that I want to begin collecting my traffic on. So the fastest way to do that then is to go down here in our main window, select the interface I want to capture, select Start, and that will bring me to my next Wireshark window, which is my capture window. Now, let me go back to my web browser again to generate some traffic, and I'll click on Chrome Web Store here just to generate some traffic, and then I'm going to close my web browser. And what we're going to see now is Wireshark began capturing a lot of traffic. And there are 3 windows in Wireshark. We have the top window. The top window is our packet list. And this shows all of the packets that were captured during our session. Now, when I say packet here, I'm referring to a generic datagram, so to speak. This packet list window is actually a combination of the frame, the packet, and the segment, and the data that was received on the interface. Wireshark tends to use a generic word for datagram that is packet. When we speak about packet, we are actually speaking about network layer packet, meaning IP addressing information. However, in Wireshark, we're using the word packet as a generic term as well. I will try to be as precise as possible when I am referring to the detail section or the packet detail in this center window of Wireshark. And here's where we see the frame itself, the entire frame, the frame header, the IP packet header, the UDP, in this case, UDP segment header, and then the application layer information. So what Wireshark does is it breaks up our datagram, or what Wireshark calls a packet, into its separate components. So we have our application layer information, transport layer information, network layer information, data link layer information, all separated out for us and translated very nicely for us. Does an outstanding job of this. Last, in the bottom window, we see the hexadecimal representation of the ones and the zeros that were received. This first column here just represents a counting number of what column we're looking in at the hexadecimal values. The last column here is the translation from binary into ASCII. And every 8 bits of binary can be translated into some ASCII value, which is nothing more than an alphanumeric character. So each alphanumeric character is represented by 8 binary bits. And we're just translating that here from the hexadecimal values into ASCII values. Any information we select up in the center window will show the appropriate bits down in the bottom window in my bytes in the packet detail. So if I just want to see my Ethernet header, I can select the Ethernet 2 information, and down in the bits it will show me just the information related to my Ethernet header. Same thing with network layer header, same thing with transport layer header, and then our application layer data. If we take a look deeper at this, if we look at our Ethernet information, our Ethernet header, as we mentioned earlier, it's going to have a source and destination MAC address. My network layer header, if I expand that, is going to have a source and destination IP address. And if I close that and expand my transport layer information, here I'm going to have a source and destination port number. And this is a DNS query, port 53. And we know that when DNS is making a query to a DNS server for an IP address resolution, it's going to use UDP at the transport layer, which is exactly what we see here, user datagram protocol. Next, we're going to take a look at capturing a ping session. So in this demonstration, I want to use Wireshark to capture a ping. And we're going to see the ping move from one workstation to another, and then we're going to see us capture it in Wireshark, and then we can analyze it. To capture my ping, I'm going to launch Wireshark. I'm going to select the interface I want to capture on, and then click Start. Next, I want to open a command prompt and send a ping to somewhere. Now I'm going to ping Google's DNS server, which is 8.8.8.8. And in my command prompt window here, I'm getting a reply from Google at 8.8.8.8. Now, after I do this, I want to go back into Wireshark, and now I want to stop my capture so I do not capture any more packets. So to stop my capture, I'm going to go up to the toolbar of Wireshark and click on the little network interface card with the X in it. And that will stop my running capture. And then I can analyze my capture. Right now, I only got a few messages back and forth, which is great. Wireshark will capture everything that's leaving my network interface card and being received by my NIC. Because of this, the Wireshark screen, we could actually end up capturing so much data in here that it will get distracting to us. Windows loves to talk to the default gateway and out to the internet. It loves it. It always wants to be talking to the cloud to see if you're registered, to see if you can connect to other workstations, to see if other devices are out there. Other applications we install on our workstation are going to send out messages to the internet as well. And this can cause some issues with trying to analyze our data. So what we can do is we can actually use this filter field up here to really granularly take a look at only what we want to see. Now, to do that, we have to understand a bit about what traffic we sent and what we want to look at. So in this case, we're going to examine the ping, and we know that our ping originated at our source IP address, which was, I'll use ipconfig in a command prompt to find out what my IP address was. My source IP address here is 192.168.170.183. And my destination IP address was pinging Google, which was pinging 8.8.8.8. So I know my source is 192.168.170.183, and my destination IP address is 8.8.8.8. So what I can do is I can write a little filter to only show me the packets that have an IP address, ip.addr, equal to 192.168.170.183. And then I also want it to match the criteria that says where the IP address is equal to 8.8.8.8. And now what this filter will do is it'll say only show me packets that have an IP address of 192.168.170.183 and 8.8.8.8. And now it only shows me the messages that I want to see. If I analyze my information here then, the very first message I see, segment number 19, we saw was sourced from my workstation, has a destination of Google. It's using protocol ICMP, Internet Control Message Protocol. This is what ping uses on a Windows workstation to send messages back and forth. It tells us the length and it tells us some info about that. If we look at our detail in the center here, we have our Ethernet frame. And our Ethernet frame was sourced from my MAC address of this workstation with a destination MAC address of, in this case, my default gateway. My IP header information now, my network layer header. In here, it will have my source and destination IP addresses, my source IP and destination IP, where I'm originating it from and where I'm pinging to. And then last, I'm going to have ICMP information. And the ICMP information that I have is going to tell me what type it is. In this case, it's an echo request. Echo is a ping, and a request is the message that my workstation sends to another. And we're going to be expecting an echo reply. It puts some data in the segment, and in this case, our data is this string of hexadecimal values, and it happens to be the alphabet, A, B, C, D, E, F, G through W, and then it repeats A through H, I. And in Windows, you can actually change the length of that payload, and it'll just make the length of that alphabet longer. If we go back up to our packet list window, the very next packet that we received is a reply from Google. Now we can see in our frame header that the destination MAC address this time is my workstation, and that ends in 5D16. Let's double check that in my IP config. So I do ipconfig/all, and I find my adapter that has the default gateway configured, and then I can find out its MAC address. I'll highlight that. It's my physical address on the Intel Pro adapter, which is 000C29AB5D16. Take a look here. 000C29AB5D16. So this frame is destined for my workstation. Take a look at the IP information. In the IP information, the source IP address is 8888 Google, And the destination IP address, 192.168.170.183, is my workstation. So this packet is destined for me. If we look at the ICMP information then, my type this time is an echo reply. So ping is replying to me. And this repeated itself 4 times because I sent out 4 echo requests and I received back 4 echo replies. So this is the basic demonstration of how I can use Wireshark then to capture ping messages leaving my workstation and then the response being sent back from, in this case, Google's server back to my workstation. In this next demonstration, I'd like to show you how to capture a website, use Wireshark to identify the 3-way handshake, and then also use filters in Wireshark to help isolate just the traffic we're looking for or eliminate traffic that we do not want to see. To do this, we're going to actually start with a very simple text-based website so you can actually see the clear text in the Wireshark capture of the website itself. And then we'll move on to a more complex website so you can see the large number of TCP sessions that are established in order to transfer a website like Google or Yahoo from their servers down to your workstation. To begin, we're going to open up Wireshark and we're going to open up a web browser. I'm using Google Chrome. In Google Chrome, we want to clear our browser history, or in any browser. Before you begin this, you want to clear your history. This way it makes sure that we're actually downloading the website from the web server and not accidentally grabbing it from cache stored locally on our workstation to display it. If we grab it from cache from our local workstation, it's not going to show up in Wireshark because we're not sending it over the network interface card. So in Google Chrome, I'll clear my browsing data from the beginning of time here. And then I can close that window and go and open up a new session of Chrome. In Wireshark then, I'm just going to begin capturing on my interface. Now, I'll go back to Google Chrome and I will browse to my very simple website, which is globalmantics.com/simple.html. And this will bring this very simple basic website up. When I'm bringing the website up, I want to then close Google Chrome, which will shut down all of my TCP sessions, and then I can go to Wireshark and stop my capture. Now we have a ton of data being transferred here from my workstation out my network interface card, and we want to reduce some of that traffic. So in order to do that, we need to find out what the IP address is of globalmantics.com so we can then write a filter just like we did for ping in order to eliminate all the traffic not destined for the web server, the globalmantics web server. So to do that, I'm going to open a command prompt and I'm going to use the nslookup command. So I type nslookup and then the domain that I want to know the IP address for. And I want to know the IP address for globalmantics.com. And what that will do is it'll return a value here under non-authoritative answers saying address 10.128.50.149 is the IP address of globalmantics.com. I can then write a filter here that says only show me packets that have an IP address with 10.128.50.149 and click apply. And now that will limit my traffic to only the conversation between my workstation and the web server. So when I'm looking at my list of packets now up in this top window, we notice that there are a lot of DNS queries happening here between my workstation and this destination 10.128.50.149. Now that's because the DNS server that I have set up for my local network is the same server as my web server. They're one machine that has 2 services running on them, DNS and web server. I want to exclude the DNS information from showing up in my packet capture list so I can only focus on the other transactions that were happening between my workstation and the web server, namely that HTTP transaction. So to do that, I can add a filter in here to say, don't include DNS information. And the way I do that is I say and, then the exclamation point. And when I do that, what's happening here is I'm saying and not DNS. So all I do is just say and not DNS and hit apply, and that will actually remove now all the DNS queries from my packet capture list here, and I can just focus on the information now related to HTTP. Another way to do this is I could say, instead of not DNS, I could also say and HTTP, saying show me only the packets that have this as one of the source or destination IP address plus HTTP in the transport layer information. And if I hit apply, unfortunately now I only get HTTP information and I do not actually get all the TCP conversation associated with that. So I'm much better off actually saying don't include DNS, because now I get the TCP protocol information in addition to the HTTP protocol information. Now when I look at my packet capture here, I'm showing all the transactions between my workstation and the web server. If I take a look, I need to identify some three-way handshakes. And I can do this because I know a three-way handshake has a SYN as a segment sent, then a SYN-ACK as a segment received, then a ACK as a segment sent. And it looks like I have multiple three-way handshakes happening here. So first of all, in segment number 274 here, if I take a look at this one, and I open up the TCP information in my packet detail window, I notice that the source port, the port that my browser chose, is 49,912. And the destination port here is port 80, my web server. So I can always check the direction of my packet flow by looking at the network layer information. The source address will be my workstation, the destination address is my web server, and that indicates that my packet is flowing from my workstation to the web server. When I look at my source and destination ports, this confirms that because my web server is operating on a destination port number of 80. And my workstation will be listening on 49,912 for the website to be received from the web server. I also see that I have a segment here that has a source port number of 49,913. Now that means there are two different TCP sessions happening here. Let's take a look at each one of these to find out where our website was transferred. If I right click now on this and select follow TCP stream, what this will do is it's going to show me every piece of data that's been sent between SYN, SYN-ACK, ACK, and FIN-ACK, ACK, FIN-ACK, ACK, or if there is no FIN-ACK, ACK, FIN-ACK, ACK, it'll show me everything that was sent up until the point that the last segment was received. And if we look here, there's lots of information about the request being made, but the critical part here is the website itself. Right here is my web page itself. This is literally the file that I have saved on my web server to create the content on that website. And if you look here, this was the same content that we saw in Google Chrome when we browsed to that site. So I know this is the site that I transferred, and I've captured the whole thing, which is outstanding. This is exactly what I wanted to do. If I close my follow TCP stream and I look through my list of segments that were sent here, I can see my SYN, SYN-ACK, ACK at the beginning to begin my TCP conversation. If I scroll to the end, I should see a FIN-ACK, ACK, FIN-ACK, ACK, and I do actually. In number 293 here, I see my FIN-ACK, then an ACK, then another FIN-ACK with this PSH, push, flag turned on here. But this is a FIN-ACK, and then last I see an ACK. So I see FIN-ACK, ACK, FIN-ACK, ACK. This push field, what that says is it says if I'm sending data back and forth between the two endpoints, in this case my workstation and my web server, if for some reason the amount of data that I need to send is less than the total amount of data sent in the window size, don't worry about it. Just acknowledge that the data was received anyway. So this has to do with how TCP is using reliable communications along with this session establishment to transfer data. And the push is just saying, don't worry how much data was sent, send the acknowledgement for it right away. So this fin push ACK is just simply a very fast way of ending the connection in this particular case. So what the point that I'm trying to make here is, when we transferred this website, we saw the SYN-SYN-ACK ACK. In the middle here now is where we're actually sending the website back and forth up until we start the FIN-ACK process, where we start shutting the session down with FIN-ACK ACK, FIN-ACK ACK. Now, if I go back to my original filter that I used, where I just said the IP address and not DNS, I said that there was another session that was established here, and that was 49.913. Let's take a look and see if there's any data transferred in that session. We can do the same thing by right-clicking and then selecting Follow TCP Stream. And if you notice here, there's no data sent at all in this. So we have blank information. So there's nothing that was sent in this particular TCP transaction. If we take a look at the capture details here, I have SYN-SYN-ACK ACK, and then almost immediately I have, well actually immediately, then I have my FIN-ACK ACK, FIN-ACK ACK. So it built the TCP session and shut it down. Why did it do this? I have no idea. It did build the session and shut it down gracefully, so we do know that in this particular case that we set up a TCP session properly and we shut it down properly. We just didn't transfer any data. This will happen in Wireshark while you're capturing websites or other TCP sessions. What will happen is our workstation will make multiple TCP connections to the web server. And sometimes we have to take a look at these multiple TCP sessions to find out where the information that's being transferred that's important to us is actually being sent. It's not sent in this one. If I once again drop down and go back to my original filter here with my IP address and not DNS and apply that, we can see that all the data was sent in 49.912. And here is that data. Let's take this a step further now and go to a more complex website. Now in this next demonstration, I want to do a more complex example. And what I'd like to take a look at is I'd like to go to the trainsignal.com website. And in the first example, I specifically chose a website and built a website that was a single IP address with a single text-based document on it, so that we could see the entire transaction happening inside of Wireshark. Now, what we're going to find when we go to a more complex website, like TrainSignal's website, is that it transfers information from multiple different web servers throughout the entire transaction process. In addition to that, we're going to see more than one TCP session opened up to each single web server that we're browsing to. Now, even though we're only going to go to one URL in our browser, that's going to use the HTTP protocol to stream an entire string of instructions that will tell our web browser to go browse to many, many, many other websites as well. So let's take a look at what's going to happen with that, and then I will explain the pieces of it and what we can actually use to troubleshoot at that point. So I'm going to start a new capture here. And then I'm just going to open a browser and browse to trainsignal.com. And I'll close my web browser and I will stop my capture. And now what I should see is I should see the entire trainsignal.com site that was transferred here. Now if I look, this is a substantially larger number of packets that I've received here than I sent in the previous example. So let's take a look and analyze what we have and see, first of all, what started the initial transaction. And the way we want to do that is we want to find out the IP address of trainsignal.com and then write a filter up here using the ip.addr filter to find the packets inside of Wireshark that contain that information. So we'll use NSLOOKUP. And we'll do trainsignal.com. And there are 3 IP addresses for trainsignal.com. So I'll write a filter for all 3 of the addresses, and we'll find out which one it actually used. 184.106.104.28. Now I can use the OR function here. Now the OR function, I use a double pipe. And the pipe key is the key directly above enter. And you have to do shift and then that key. It's the same key that also has backslash on it. So I'll do the second address, 50.57.186.202. And the last one, that OR again, 50.57.186.253. And I didn't put my IP.addr in there. Equals. There we go. And we always know our filter is good when the background of the filter turns green. If I have something off, where I don't have the character in there right, here I deleted the equal sign, it immediately turns to that pinkish or reddish color, which means that your filter is wrong. If you apply it, nothing will happen. Once we get it all green, that means we're good to go. And that OR statement here is saying look for the 184.106.104.28 IP address or the 50.57.186.202 IP address or the .253 address over here. So one of these 3 it will filter on. And it looks like when we connected to the 184.106.104.128 IP address. So let's take a look at what we can glean from this and see how the transaction progressed. So the first thing we want to check for is to see if the 3-way handshake occurred and if it was successful. Because without the 3-way handshake, we are unable to send data. So let's take a look. So it looks like we tried to set up 3 separate TCP sessions here. One for 49.337, one for 49.338, and one for 49.339. Now remember, those are the ephemeral port numbers, the source port numbers sent from my workstation to the trainsignal.com website. And we're trying to connect on port HTTP. So we sent out 3 SYNs. And we received a SYN-ACK back for 49.337. And actually, if we jump down a few here, we actually received it back for 38 and 39 as well. And then we went ahead and acknowledged then for 37, 38, and 39. Let's take a look at this GET here that happened. So this must be happening on port 49.337. And the reason I'm able to tell that is that 49.337, that ephemeral port number, is the only one where we've done a SYN-ACK so far. So up here, here's our 49.337 SYN. Here's our 49.337 SYN-ACK, and then here is the ACK return. Now remember, in my filter up here, I can add in the TCP port number and say and where the TCP port is equal to 49.337. And I'll apply that. And now we can check to see if that first GET actually operated on that port. And it appears that it has, because the filter matches on that port. If we take a look down in our TCP section for the transport layer, we do see that the source port is actually 49.337. And this is the GET request saying, please send me www.trainsignal.com. Send me the data for that website. So now what I see is I see the 3-way handshake occurring, and then I see a bunch of data being sent. I can do the follow TCP stream here, but we're most likely going to just see gibberish, as the website is compressed severely using the HTTP 1.1. In addition, this may not even be text that it's transferring. It could be some JavaScript or other code that's being sent back and forth between the web server and the web browser. So we may not be able to interpret that at all. Essentially what we're seeing there is those are the instructions that are being sent to load the rest of the website. So let's take a look and see what else we can glean from our transfer here of this data in and of itself. So if while we're browsing through here, If we're paying attention to the packet number in the list here, we jump from packet number 117 to 352. So something happened in between there, and most likely we sent more website, but we probably connected on a different IP address to do that. Let me leave my cursor and select segment number 117 here, and then I will clear my filter. And when I clear my filter, what will happen is it'll show me the very next transaction that happened right after 117. And it looks like we're getting a SYN-ACK back from the server. So let's scroll up a little bit and see if we can find the SYN that was sent. Now the SYN should be sent from this case from 93.184.216.139. So let's see if we can find the rest of that. I'll put a filter in here. And now we can see all the transactions for that. And it looks like my IP address once again connected to 93.184.216.139, this time on port 49355. We're going to this IP address though, this public IP that we haven't seen before, and it wasn't one of TrainSignal's websites that it resolved. And if we look, quite a bit of data was sent here with a bunch of resets at the end. Let's see if we can resolve that IP address into a domain name by using NSLOOKUP. Typically, when we set up a DNS server, we put in both a forward lookup and a reverse lookup. The forward lookup is so that we can do a URL to IP address translation. The reverse lookup is so we can do IP address to domain name. The reverse lookup isn't required for the website to work, so it's not always set up. Let's see if we can get any information out of this here. NSLOOKUP 93.184.216.139. And this is saying no, there's no information. And I'm using Google's public DNS server. There's one other way we can check this out. If we do open a web browser and we say who is, oftentimes we can, here we're using whois.net. We can type that IP address in here, and sometimes it will return who owns that IP address. 93.184.216.139. And it says network name Edgecast. It's a network block. Just from examining this, this appears to be an ISP. There's not much information we can glean from this type of lookup. So we're really not sure what this IP address is. What I suspect is that TrainSignal is using some cloud-based services to host some of its content. So it's probably browsing to those IP addresses to connect and establish the TCP sessions. And we just don't have the reverse lookup set up for that particular IP address. Yeah, in this case, it looks like since we see some TLS information in here, TLS is transport layer security, means that this information is encrypted. If I follow my TCP stream here, well, we seriously are going to see some gibberish on this. Although I do see some information, we see some VeriSign information. That's the exchange of the certificate in order to build the encryption. And then it looks like there's some clear text information here about Twitter and whatnot and some other sites. If you wanted, you could dig into these to find out what these are for. You could probably Google for them and it'll tell you. Additionally, if you use some of the plugins and add-ons you can get for Wireshark, that may help you interpret that as well. Now, the question here then is, how are we going to use this for troubleshooting? Well, all of this really shows us is that we definitely have three-way handshakes occurring. Here we see the SYN, SYN-ACK, ACK, and then a bunch of data being transferred. In all of the other previous filters that I've applied to this, we've demonstrated that there is a three-way handshake and then data being transferred. This is the key, and this is going to tell us whether the problem exists at the transport layer or lower, or the application layer and higher. If the three-way handshake is occurring, That means that we have a connection at the transport layer, and there is no problem happening below the transport layer. So an example there is we try to browse to a website and the website doesn't load properly. And one of the issues there could be that the TCP session is not being built. So if we go into Wireshark and we capture the problematic website, what we can look for is if the three-way handshake is occurring, that means that the connection from the physical layer, data link layer, network layer, and transport layer, all that communication is solid, and that the problem must exist at the application layer or higher. If the problem was occurring because the three-way handshake was not happening, we would immediately see that in Wireshark. If the three-way handshake did not complete, we definitely cannot have any application layer traffic passing. So if the problem then existed at the transport layer and below, we would not see the three-way handshake occur. Therefore, we would start looking for our problem in a firewall setting, either on a Windows workstation or on a router or a firewall itself. And we begin looking there for the problem. So to wrap this up, when we're looking at this complex website, really, like I said, we're looking for that three-way handshake to occur. If we know the three-way handshake is occurring and our website is still not loading properly, we need to go take a look at the web server and see what's happening with the web server itself. But if we're not getting the three-way handshake, then we know that we need to go check our firewall. Now this wraps up the demonstration of Wireshark. I look forward to seeing you in future videos.